Hello guys, and welcome back to lesson 10. We are now in implicit differentiation. So let's begin. Okay, so for our definition, let's start with this idea. What is implicit differentiation? When we say implicit differentiation, it is actually a process used to solve for the derivative of equations of at least two variables. So what we did in our previous lessons, in our previous videos, is to do an explicit differentiation. We have the explicit differentiation. Okay, explicit differentiation, it implies that our function is already given. It's always a y with respect to a function of x. So all of the given are functions. Okay, but not all the time we're given with a function. Sometimes we're given with an equation of at least two variables. So let's try to have an example. Let's have the equation of a circle. Okay, so take note, this is the equation of a circle, which is x squared plus y squared equals 1. Specifically, this is an equation of a unit circle. Okay, and what if we're asked to find the derivative of y with respect to x? Okay, so let's say we're going to get the derivative of this equation with respect to x. Okay, so to do that, we need to get the derivative of both sides of the equation. Okay, so we simply apply our concept of derivative in the context of equations. Okay, and take note, you can use the rules here, so we can get the derivative of both, derivative of 1 with respect to x. So take note, we must be observant with the variable. Okay, with what's the variable to get the derivative from. So in this scenario, we have x. So the derivative of 1 with respect to x is just 0. And then we can actually apply the sum rule for derivatives for x squared and y squared. Okay, derivative of x squared with respect to x, so there is no problem. It's simply applying the power rule, which will give us 2x. But for y squared rather, okay, applying the power rule here, this will give us 2y. But take note that the variables are not the same. We have x and y in this scenario. So we need to get the derivative of that variable with respect to y. That's why we'll have this here, dy dx. Okay, so again, the variables are not the same. That's why we'll get dy dx. So we apply the power rule, then have this dy dx here. Okay, then again, our goal is to get the derivative of y with respect to x. We just need to get the derivative of the equation. So here there's a note, we are getting the derivative with respect to x, but the variable here is y, so that's the reason why there's dy dx. Okay, so we use the property of equality, addition property of equality. So 2x is transferred from the left to the right, and we have the negative 2x now, and then divide it by 2y both sides, so that dy dx will be left alone in the left side of the equation, and cancel out 2. We'll get negative x over y, and this is already the derivative of our given with respect to x. Okay, so for example, you're given a point. Let's say our point is 1 and 2. So we can substitute this point here to get our desired derivative or desired slope of the line, okay, tangent to our equation. So we'll have this is our x, 1 is our x, 2 is our y. So you will have 1 over 2. Example, that's an example of if you have a point. Okay, Okay, so let's proceed to our next example. Note that the goal is to have dy dx, or the derivative, with respect to the desired variable. So in case you're given two variables, so it's always dy dx if it's not stated. Okay, so if it's stated, you're just going to get dy dx. But if it's stated to get some other derivatives, for example, there are three variables, we're asked to find dz over dx, so you'll get the dz over dx instead of dy over dx. Okay, so for example, let's have this. By the way, this is a proof for arcsine. So how do we get the formula for arcsine? So remember, this is the formula for the derivative of arcsine, and we're going to prove that this is the formula using our implicit differentiation. Okay, so note that y is arcsine of x. Okay, our function here is arcsine of x, and remember, this is an inverse function, so we can actually rewrite the inverse of that function as sine y equals x. Okay, so again, the answer for arcsine is actually the angle, which is y. Okay, and our x is the ratio, so that's why we have sine y, our angle, equals x. So we can actually transform the equation here, or rather the function here, into its original function, not the inverse function. So using implicit differentiation, let's try to get the derivative of this equation with respect to x. Okay, with respect to x. So again, derivative of sine is just cosine. So we have cosine y, but take note the variable is y, and we're getting the derivative with respect to x, so there is actually dy dx because the variables are not the same. Okay, and then derivative of x with respect to x is just 1. Okay, divide cos y, both sides, you will get dy dx equals 1 over cos y. So we have now our dy dx here. Okay, take note that cos y is square root of 1 minus sine squared of y. Okay, so from Pythagorean identities, so I'll try to write the Pythagorean identity here. So we have sine squared theta plus cos squared theta equals 1. So if we try to look for cosine, you have 1 minus sine squared theta, then get the square root of both sides, you'll have square root of 1 minus sine squared theta. So that's how we got this. Okay, so let's continue. So substituting this identity, we'll get 1 over square root of 1 minus sine squared y. So actually, if you try to look at the formula, it's almost the derivative itself. Okay, but take note that our y, okay, from our previous post, y is arcsine of x. Okay, y is arcsine of x, so that's why we substitute arcsine of x, so that all of our variables already with respect to x. So take note the variable here is x and not y, so that's why we need to have arcsine of x here instead of y. Okay, and then remember, if it's squared, sine squared, it's just the entirety is actually squared. Okay, and take note that the sign of arcsine of x is just x. Okay, why? It's because the function of the inverse function is just the given variable. Okay, so remember this f composite of f inverse. If we have x here and then if we have x here, this is just x. Okay, so that's why sine of arcsine of x is just x. So we have 1 over square root of 1 minus x squared, and if we try to generalize this, you'll get 1 over square root of 1 minus u squared du dx, being the derivative of arcsine. Okay, so that's how we got the formula for arcsine. Okay, so note for the proof of arc cosine, it is actually just similar in process, but instead of cosine y, we'll have negative sine y, because the derivative of cosine is y, and then instead of cos y, we have sine y equals square root of 1 minus cos squared y. So basically you just substitute everything here with these two, and of course whatever is your y there, which is, I think y is arc cos of x rather, okay, not I think, but it's arc cos of x, and you'll still get the same formula but the negative version of that. You have negative 1 over square root of 1 minus x squared. Okay, next let's try to look at the proof for arctan. So take note that the formula for the derivative of arctangent of x is 1 over 1 plus x squared. So it's almost similar to the previous example actually. So we have y equals arctan of x, then get the original function, which is tan y equals x, and then get the derivative of tan y, which is secant squared of y, and we have dy dx, of course, because the variable is y. Derivative of x is just 1 with respect to x, and then we divide by secant squared y both sides, so we have 1 over secant squared y. Okay, so take note, in the Pythagorean identities also, we have secant squared y equals 1 plus tan squared y. Substitute the identity, so we'll have 1 over 1 plus tan squared y. Then of course our y is arctan of x, so take note, our goal is to have a derivative with respect to x and not y. That's why we substitute the value of y, which is arctan of x. Okay, and then okay, so it's actually the square, and tan of arctan of x is just x. So that's why we have 1 over 1 plus x squared, and if we try to generalize, the derivative of arctan is 1 over 1 plus u squared du over dx. Okay, so that's how we got the formula for arctan. So of course the proof of arccot is similar, but instead of secant squared y, we have negative cosecant squared y, and of course the identity of cosecant squared y being 1 plus cotangent squared y. So you'll have negative 1 over 1 plus x squared as a result. And then we have the arcsecant. Okay, so the arcsecant is quite longer to prove because of this absolute value of x. Okay, so we'll have the same process, transforming the inverse function to its original function, being secant y equals x. Get the derivative, and remember the derivative of secant is secant tangent. Okay, divide both sides by secant y tangent y, and you'll get this 1 over secant y tangent y. So take note that tangent of y, so Pythagorean identities again, is just square root of secant squared y minus 1. So we substitute, then we'll get this. Okay, so we substitute the value of y so that it's already with respect to x, variable x, and take note that the secant of arcsecant rather is always positive. Okay, so again take note that the arcsecant is always positive. This is the graph for you to look at. Okay, so the output of secant is always in the positive side. There are no negative outputs, so arcsecant rather. So that's the answer for arcsecant. It's always positive. That's why we'll get the absolute value of x. So secant here becomes absolute value of x because it's always positive. And then if we continue, our secant of arcsecant is actually x also, which is x squared, and this is the formula for the arcsecant. And if we try to generalize, the formula is this. Okay, so if you try to check your formulas for the derivative of arcsecant, this is the derivative of arcsecant. Okay, so take note that the process for cosecant for cosecant is similar to this, but instead of having secant tangent, we have negative cosecant y cotangent to y, and we are going to use cotangent to y equals square root of x cosecant squared y minus 1 in our proof. Okay, so let's have another example. So what if we're asked to find the equation of the tangent line? So take note, this is already an equation, not a numeric function. So we have y squared equals e to the power of 2x equals 3y plus x squared, and then we're given a point 0, 3. Okay, so first let's check if the equation exists in 0, 3. So if it exists, or rather if the both sides left and the right are equal, so they exist. If it's not, then it does not exist. So substituting the values 0 and 3, okay, respectively, for our variables here, we'll get 3. So this implies that our equation is true. The point exists in the equation. Hence, we can now proceed to implicit differentiation. Okay? So we'll get the derivative of both sides with respect to x. So again, there is nothing stated here what variable. So the standard variable is x because x is our most often times the input variable. Okay, so getting the derivative of both sides. So take note that the derivative of y squared e to the power of 2x, we'll use product rule here. Product rule. So this is our u, this is our v. That's why we have this. So u dv plus v du. Okay, this is u dv plus v du. Then of course, for the right side, it's very easy to get the derivative. So we have the derivative of 3y, that is 3. Then of course, derivative of y is with respect to x is just 1, but there's also y, so we have dy dx. Then derivative of x squared is just 2x. So our focus already at the left side of the equation. So we'll get the derivative of e to the power of 2x, which is e to the power of 2x plus times 2. Okay. Then derivative of y squared is 2y. Then of course the variables are not the same. Okay. So we'll have dy dx again. And then we continue. So simplify further, we rearrange. So we have 2y squared e to the power of 2x plus 2y e to the power of 2x dy dx equals 3 dy dx plus 2x. Our goal is to have dy dx at the left side, and then all of the other terms will be found at the right side of the equation. So we have this. Okay, so we transfer all of the dy dx, so terms containing dy dx. So if it's not very obvious, so this and this will be at the left side, this and this will be at the right side of the equation. So here 3y dx, it's transferred to the left, becomes negative 3 dy dx, and here 2y squared e to the power of 2x, if transferred to the right, will become negative 2y squared e to the power of 2x. Okay, that's why we have this here. Okay, and then we can factor out dy dx, the left side, divide it by 2y e to the power of 2x minus 3 both sides, so that dy dx will remain at the left side, so no other terms aside from dy dx, and this will be our derivative. Okay, the formula for the derivative of our equation. Then we substitute. To take note that the equation of the tangent line, we're going to apply the point slope formula. So we also need the slope of the tangent line. So the slope of the tangent line is dy dx, but we're going to substitute 0 and 3. Okay, so this notation here is simply saying that we're going to substitute 0 and 3. So this is our formula, and if we substitute 0 and 3, we have this, and the result is 6. Okay, and this is the point slope formula. We have y sub 1 and x sub 1 from here, 0, 3, and this is our x sub 1, this is our y sub 1. So we substitute the values of x sub 1, y sub 1, and m sub t. and then simplify, and we'll get 6x minus y plus 3, and this is the equation of the tangent line. Okay, so let's have another example. So for example, you are asked to find this. Differentiate the equation 3x squared minus 2y cubed plus 2z to the power of 4 equals 3t with respect to z. So again, just get the derivative with respect to z, and then we're actually, how many variables? 1, 2, 3, 4. So we have 4 variables here, and we don't know which is the input functions or the input of the function or the output of the function here. So of course, this is not a function, this is an equation. So let's just get the derivative of the equation as is. So instead of dx, we have now dz. So observe, it's all dz. So again, this is an equation, not a function. So treat it like an equation. So get the derivative of each term. So we have 6x, okay, for our first term. Then take note that it's x and z, so we will have dx dz. Okay, and then for 2y cubed, so we'll have 6y squared. Then we have dy dz. For 2z to the power of 4, okay, since they are both z, so there's no need to write dz over dz or dz dz. Okay, so it's just as is, it's just 1. So 8z cubed. Then for 3t, we have 3 dt dz. Okay, and this is already the answer. We don't need to solve for anything because it was not asked for us to solve for whatever is the function, okay, or whatever is the equation that we want to solve. So this is the final answer. Okay, so what if we're asked specifically, for example here we have dy dx of this equation, tangent of x squared y to the power of 4 equals 3x plus y squared, and we will use implicit differentiation. So again, just get the derivative of both sides. Derivative of tangent is secant squared. Okay, so we have secant squared x squared y to the 4th. Then get the derivative of whatever is inside the parenthesis or the angle. Derivative of 3x with respect to x is just 3. Derivative of y squared with respect to x is 2y dy dx. And of course, inside we have x squared y to the 4th, so we're going to apply product rule. So that's why we have x squared dy to the 4th with respect to x plus y to the 4th dx squared with respect to x. And if we solve further, so we'll get x squared 4y cubed dy dx plus y to the 4th 2x. So we distribute secant, okay, to our terms here. So we'll get this. Okay, and then again our goal is to have dy dx, find dy dx. So we'll transfer all dy dx to this side, then all that does not contain dy dx to the right side. That's why we'll have this. Okay, so all the terms containing dy dx already at the left side, and all the terms without dy dx already at the right side. Okay, so then we factor out dy dx and divide the remaining term to our equation, so we'll get this. And this is already our answer. Okay, so that's all for implicit differentiation and for lesson 10. So I hope you've learned something. See you in the next series of videos. Bye-bye.